Hi. So let's continue on the topic 2.6.2. We finish this topic on this part doing this notation. Let me scroll up. Um, we saw all this. Okay. Topic 2.6.2, how you can represent a pure rotation around a fixed axis. And we do not finish this topic yet. So we will finish on this video. And this video also is gonna be an opportunity to present the characteristic matrix of the pure rotation movement, which is done around the axis X, Y, and Z with some respective angle. And on this video, I'm gonna draw these axis systems, and I'm gonna use the tool that we've got here to try to show how this rotation occurs. Okay, so let's get started. Um, Let me explain to you this matrix, and why these terms. Okay, so I'm gonna draw the XYZ coordinate system. The axis Z, the axis X, and the axis Y. And link it on this axis system, which is a reference system, is another referential system. And let me draw here. And doing this, I'm gonna be able to explain to you the pure rotation movement. You're going to see how it's done. N O A, and now let me draw again right here, and I'm gonna rotate this axis, this referential system. And now let me pass a dashed line after the rotation. Okay. So this matrix is a characteristic matrix, which means a pure rotation movement. And let me copy this, and no, sorry. Let me drag down this a little bit. Okay, now let me drag down this. So on this column, we have the axis x, the axis y, and the axis z. And this ref system F and OA um, is formed by these unit vectors, and these unit vectors, the length of these unit vectors is 1. So this reference system F and OA link it on this another reference system F X Y Z. The unit vector n is above the axis x, and can you tell me what are the other values for these terms, as they are not this vector a and o, both of them are also respectively on above some axis. Right here we have the unit vector a above and pointing in the same direction as the axis z, but on this column is just for x, and as these unit vectors, they are not decomposed on the axis x, we do not have any value for these unit vectors on this column. Okay, now for this column y, we have right here y, the axis y, but now I'm gonna have to draw a vector or a point. On the last video we saw that a point can be tracked as this point is linked on it, this ref system. We can also have a rigid body, and when this rigid body is linked on it, this ref system, we are able to track all the orientation and position of this rigid body. So let me draw a vector, and on this vector we can have a point, a rigid body. Let's say that is a point P, as we were talking on the last video. As this matrix is characteristic of a pure rotation on the axis x, what's going to happen is that now I'm gonna, this is what is happening. Now let's say we are applying a rotation movement. See, if we apply a rotation movement, but only on the axis, but above the axis x, so this axis, we do not have any change on position or rotation, but the unit vectors of this referential system, A and O, they will change. So let me see this. Okay, the rotation is above the axis x, and the vector n will do not have any change. And now moving the reference system F and OA. Can you see? I'm gonna paint this. Let's paint green. Okay, so now after the rotation, the final position of the unit vectors of this referential system, they're going to look like this. And because the vectors on the x on this on the x y z axis, oh, oh sorry, okay, on the axis x we will not have any change, okay, because the transformation of pure rotation is made it above this axis. And that means any decomposition of the point or vector on the xyz coordinates, but for the axis y we have the decomposition. So after the rotation, I'm gonna keep with the color green. Okay, so we have to decomposing cosines and sine components. And right here, we will have some angle theta. So is cosine of theta point on the unit vector O, the point P, and for this one is going to be the decomposition of the point on the axis, on the unit vector A, which will be times the sine of theta. Okay, cosine and sine. And the same for the axis Z. Hope you got it. What I wanted to do on this video is to show you the types of pure rotation matrix that we have. Those are characteristic matrices for pure rotation movement. And it's very important to you to understand. And just by looking at it, you have to know what type of movement this rigid body or vector or a point is doing just by looking the matrix. Let me keep going. So if you wanted to find the final position or rotation of a point P, link it on a referential system, we just need to After the rotation movement, because is the context that we are talking. So you are applying a rotation movement above the XZ, and this rotation it has some specific data angle, and multiplying by the coordinate system that is also that this point is referenced. And we've got another notation, um, not to find the point, but to represent this characteristic matrix. When we are representing a rotation movement above the axis x, and this rotation movement will produce a angle theta, and now you know why these values. And right here on this notation, we do not need to write uh, cosine completely. We just need to write C and theta. And for the sine is the same. We just need to write S and theta. And look at the first videos, and we will saw why this signal of minus, please. So that is the notation for a pure rotation movement done above the axis x, and a pure rotation movement above the axis y, and is the same concept. Again, so you have to be able to know what type of movement uh, is being done just by looking at the characteristic matrix. Cosine of theta. And a rotation movement, a pure rotation movement above the axis z. Cosine of theta, sine of theta, 0, minus sine of theta, cosine of theta, 0, 0, 0, 1. Right here, a pure rotation movement above the axis y. So let's see right here. The pure rotation movement is being done around this axis, and if we do this, E O N But as we are applying above this axis, it will not have any change. So for y, can you see? Okay, it's 0 because the rotation is being done above this axis, so we do not have any change. And rotating this axis, hope you got it. And we also can write this equation uh, in other form, which is the form that we're going to use from now on. Uh, we will see this notation from now on very often. And what is that means? Uh, that means the transformation of the referential in relation to a universe. Okay? And this term we will write as P, or which is P in relation to the referential R, and we write this as P in relation to the referential U. So let's rewrite this equation. Which is using the notations that we're going to use from now on. Which is much nicer also. And now let's finish solving the example 2.7. It says that a point P, and it gives us the rotation of the point, and this point is coupled or linked on a rotation referential, and these referential are spinning with some theta of 90 degrees around the axis x of the referential system. So at this point, you are able to draw just by reading the context. It's very easy. We have our referential system, which is a coordinate system. And this referential system will be linked, sorry, other referential system will be linked on this one. Let's say this is the referential system f, x, y, z, and we will link right here other reference system. And it asks for us to find the coordinates of the point in relation to the reference system after the rotation movement. So let's draw the other referential system. In this referential system, it will spin or turns 90 degrees. I'm gonna pass a dashed line above the axis, the unit vector or axis A, and the rotation is 90 degrees. Rotation of 90 degrees. So I don't know, 45, 90, and it will look like this. Let me do it again, but I'm gonna place this F in OA referential system. I'm gonna place it right here. And now I'm gonna do this movement. Actually, the axes or unit vectors a and o, they will be, as I'm looking on the book, only the vector unit vector a will not be above some axis. Okay, I'm gonna draw the vector, or sorry, a point that can be tracked if we link it on the reference system. And this point, it has these coordinates, 2, 3, and 4. We are able to track based on the reference system. And remember what I say, we are able to find the final orientation position of a point when this point is referenced to a referential system, as we are doing. And also remember the form of a characteristic matrix of a pure rotation movement above the axis Z, which is this one. So it's very simple. We just need to apply this formula, and we will find the final position orientation of the point linked on the referential system. Px, the coordinates Px, Py, and Pz. We just need to apply the rotation movement. Applying a rotation movement. This theory is not only for robots. Imagine a aircraft um, is the same thing. And this is very nice because of this. We can apply in a bunch of different things. And when we do cosine of 90 sine of 90 degrees, and 0, 1. Now applying these values right here. Final, okay, final position, orientation, the pure rotation transformation, and the referential system, ref system, and realize we are able to track this point when it's linked on this ref system, and Because of this, we know the initial and final position. Very simple. At this point, so we will be obtain the following. And the final position, okay, so now we just need to substitute these coordinates on the XYZ ref system, and that's it. Now I have already drawn how you can manipulate these transformations on the access system. Okay, on the next video, we will talk about how you can represent the transformation of pure rotation together with the translation transformation. So is sorry, I said pure translation or pure rotation. We have pure rotation, pure rods, we have pure translation. So remember a telescope which has different stages. It's like a translation is this. You're changing uh, this position for this position, and rotation is when we are spinning uh, the rigid body or a pointed or a point fixed on the reference system or a vector, and we have translation together with the rotation, which is the subject that we'll discuss on the next video. So that's all. Thank you.